Okay, welcome back for our next talk. It's a pleasure to have Sebastian Mizera talking about crossing. Please go ahead.
Okay, thank you, Matthias, and thank you so much for the invitation to this conference. It's really a pleasure to be here. So I wanted to start with a quick lesson from history, which is that this year we're actually celebrating the 80th anniversary of one of the very first Feynman diagrams, which looked like this, and it appeared in this paper of Stuckelberg in 1941. That, however, wasn't even the most exciting part of this paper. In the very same paper, he made a revolutionary at the time observation that particles are indistinguishable from antiparticles with the opposite energy and momentum. At the level of observables in the quantum field theory, this translates to the property called the crossing symmetry for the full S matrix. This means that we consider S matrix elements with arbitrary states, except for the fact that we couple one on one side to a particle and on the other side to an antiparticle with the opposite momentum. And then the question is whether the two scattering processes are related by analytic continuation. That question has remained an open problem since its introduction by Gell-Mann and collaborators many years ago. At this stage, let me emphasize that sometimes people use the term crossing symmetry to really mean permutation invariance, and this is definitely not what I will be talking about today. The reason why this question is so difficult is very much tied to the unfinished business within the S matrix theory, which is that we can ask the following question: what analytic properties of the S matrix guarantee that that S matrix corresponds to a causal scattering process in space-time? Okay, we still don't know a general answer to this question. And basically, previous attempts at proving crossing symmetry failed essentially because within the LSZ formalism, just the notions of the on-shell S matrix and the space-time causality are intrinsically incompatible with each other. So this is probably a sign that we need a better formulation of S matrix. For example, there's been a lot of work at the coming from flat space limit of ADS-CFT. So let me first explain this tension between S matrix and space-time causality on a toy model. Let's say we have some causal signal. So in the time domain, it was caused by something at time equals 0, and then the signal propagates in the positive axis. Now what we can ask is, let's do a Fourier transform to the energy space. So the notion of causality here boils down to the fact that we integrate from 0 to infinity. Okay, and unfortunately, this integral here only exists when the imaginary part of the energy is strictly positive. And this is required by exponential suppression of this integral as time goes to infinity, at least for polynomially bounded signals. And that property itself is incompatible with dispersion relations, or which for our purposes is a toy model for on-shell conditions, which simply say that the square of the energy is some non-negative constant. Okay, if we just look at the reason why is we can just look at the imaginary part of this constraint, which is given by the imaginary part of E, which we already know has to be positive. So that constraint imposes that the real part of the energy has to be 0. Then on the other hand, we can look at the real part of this constraint, which tells us that we subtract 0 minus something strictly positive. And that means that this equation here is in direct contradiction with the dispersion relations. So this tells us that we're basically forced to first compute the unphysical F tilde and then define the physical value by analytic continuation. In this case, it turns out that the analytic continuation is actually extremely simple because you can just approach the real signal from the upper half plane. Of course, this changes drastically, as you might expect in quantum field theory. So the version of causality that you can use at this stage is the so-called microcausality, which just tells us that the operators commute at space-like separations. Of course, at this stage, we're not only assuming causality, but built in, we also have the notion of locality, just existence of local operators, And for the arguments to work, you also need to employ unitarity. Now the problem becomes extremely severe. And as we've learned in our toy model, just the integral Fourier transform of some correlation functions just does not exist on shell, meaning that it does not exist when the masses are physical. And then what you need to do to compute the S matrix is you need to do analytic continuation. Despite what you might learn in QFT books, this is actually not a limit, it's an analytic continuation. And the reason why, so basically we need to understand all of the physics of the S matrix by supposed analytic continuation across the light cone. So you start with something that does not have support on shell, it's only defined, say, for tachyon scattering, ironically, or when the masses are imaginary. And then the question is, can we continue that to a physical value of kinematics? And to my surprise, you can ask the questions, does it always exist? Is it unique? Why not? And such questions actually do not currently have general answers. So let me summarize what is actually known so far. So this is progress in the last century. What you can do is you can, in order to start answering such questions, is you can exclude, first of all, the massless particles. You can confine yourself to 4-point scattering. So you also exclude the higher point processes, and you forget about the notion of crossing of a single particle. Once you do this, the result is that the previous arguments guarantee that there exists analytic continuation such that there are possible singularities everywhere in the upper half plane, except for infinitesimal neighborhood of physical regions. Some are here and some are here, and infinitesimal neighborhood of infinity. So this is the energy plane at the fixed momentum transfer. So then if you wanted to prove a crossing-like relation, you would start somewhere here, then you would go to asymptotically large energies beyond the Planck scale, and then you would have to continue that to the other channel. So this is, this kind of analyticity statements are due to the work of Bros and collaborators starting in the 60s. Let me emphasize at this stage that if the so-called Euclidean regime would exist, the problem would be essentially trivial, but unfortunately for a generic S matrix element, it does not. And this is the reason for the whole source of complications. So at this stage, this leaves us with many unanswered questions. For example, you can ask, can we identify what kind of singularities are absent and what is the physical reason for that? Whether the connection to the asymptotic kinematics is accidental, and can we say anything about finite energy, constraints of causality at finite energies? Similarly, can we separate the assumptions of causality from those of locality? As we know, we would have to do that to learn something about quantum gravity. Most importantly, there's a question whether we can actually generalize this to higher multiplicity, to include massless particles, and so on. And finally, can we realize the dream of Stuckelberg and prove that you can connect a S matrix element with a particle to that with a single antiparticle? So hopefully I convinced you that we need a new strategy. And the strategy will be basically to go back to where it all started, and to Feynman diagrams, and reconsider the problem of crossing symmetry within the framework of perturbation theory, and more precisely within the wordline formalism. So despite the fact that we'll be working in perturbation theory, the goal is still to make claims or make proofs which will be valid to all loop orders at any multiplicity for all spins and masses. And one of the advantages of using perturbation theory is that we can separate the questions of analyticity from those of UV and IR singularities, which is something that you cannot do non-perturbatively. And we'll confine ourselves to any theory in larger than 2 dimensions that satisfies CPT, namely that the Feynman rules are crossing invariant, which of course by no means guarantees that the Feynman integrals are also crossing symmetric. So the simplification that comes from perturbation theory is that there's a clear connection between singularities of the S matrix and the wordline saddle points. And the reason why this is important is that we convert what used to be an analytic statement into an algebraic problem. It's algebraic because we have well-defined equations for the saddle points. So let me quickly remind you how a contribution from a single Feynman diagram look like in the wordline. So we integrate over Schwinger parameters alpha for each of the internal edges. We can have some, in principle, polynomial numerator coming from some interesting physical interactions that you can have depending on the matter content. But for us, the most important part will be this, what I call V in here, which is the wordline action. If you're not familiar with this formalism, let me just tell you that the action is simply proportional to the ratio of Semantic polynomials f and u. And now the Feynman-Iapson prescription, the one that the causal Iapson prescription, or equivalently, the convergence of this integral at infinity is imposed by requiring that the imaginary part of the action is strictly positive. Unlike in the non-perturbative approaches, this is actually what guarantees that we land on the physical prescription, meaning the one guaranteed by the causal Feynman-Iapson. Okay, and now the singularities exist in the classical limit, which are simply dominated by the saddle points. So the saddle point equations are very easy. There are bulk saddles, so they're just given by variation of the action with respect to all of the Schwinger parameters and setting that to 0. And it turns out there are also boundary saddles, which come when you approach the boundary of integration at alpha, the Schwinger parameters going to 0. This is, you can show that this is another way of formulating so-called Landau equations that I think most of you are familiar with, which simply tell us to impose on-shell conditions on all internal propagators, where Q sub B denotes a momentum and M is the mass of a running through a single edge. So these singularities are also known as the anomalous thresholds or normal thresholds in the special case, and they're intrinsically Lorentzian phenomena. And at least partially, they encode causality constraints within perturbation theory. Another way of thinking about them is that they answer the question of how complicated scattering amplitudes can be. So a lot has been studied about the complications sort of in this direction, about how complicated functions can we get out of Feynman integrals, as we've seen in the previous talk. And then another question that you can ask is how complicated the arguments of those functions could be. And in particular, one question that you can ask is, can they be always written in a closed form? And my conjecture is that the answer to this question will be no. So let's illustrate this at a simple example at 3 loops. Let's consider this envelope Feynman diagram, where in principle you can allow different masses for the internal and external states. So in the special case, when you confine yourself to all massless particles, you find the following in a more fashionable notation. The alphabet of singularities is that S, T, or U can be equal to 0. Now you can ask, how does it generalize when you go to massive scattering? And this actually grows drastically. This is the singularity locus of your Feynman integral. It actually turns out to be a degree 128 curve in the kinematic space. In fact, this curve is so large that it would be impossible for me to fit it on a single slide. For example, the last component here has 300 plus terms. If you asked me a year ago how to determine this, I would say it's completely impossible. And this is the reason why we wrote a package called landau.jl together with Simon Tellen, which should be out on archive hopefully very soon, which allows you to answer such questions in more generality. If you would like to look at the more graphical version of illustrating this, this is the singularity locus of the diagram that was on the previous slide. And one of the surprising parts to me was that even if you consider the scattering process for order 1 masses, unit masses or close to 1, then the effects of anomalous thresholds seem to be actually propagating across many orders of magnitude in the energy variables S and T. And while many of these branches of the singularities lie on unphysical sheets here in blue, there are multiple components that here in orange that are on the physical sheet, and also those that intersect the physical kinematics that you would find in a real scattering experiment. Luckily for us, for the specific question of crossing symmetry, we don't need to know about the specific structure of the singularities. We only need to know about where those singularities cannot appear, because we want to constrain the analyticity structure. So as pointed out by Witten, only a certain class of anomalous thresholds can actually pose a potential obstruction to crossing symmetry. And this is how they look like. If you consider your Feynman diagram, where all of the internal edges are aligned along two beams at some finite energy, and they exchange some possible massless states. Okay, so the question will be whether such singularities can appear in your scattering amplitudes. If the answer is no, then this will guarantee crossing symmetry. So to understand why this is the case, we first need to figure out how to avoid, first of all, real singularities, and secondly, complex singularities. So real singularities are the ones that you can cross when you change kinematics within a given physical region. But then ultimately what you want to do is cross between different physical regions in the complex domains. And there you need to understand complex singularities. So let me first of all focus on the real ones. Okay, so here we know already that what we need to impose is that the imaginary part of the action is strictly positive. And this can be done by simply giving word lines infinitesimal phases. So you just rotate them by a phase, which is proportional to the variation of the action with respect to the specific Schwinger parameter. What you can show is the following this deformation, the action acquires a small non-negative imaginary part, which is to leading orders looks like this. We know that this factor is positive because it's a Schwinger parameter, and we have a square of something. So we learned that this imposes the correct I-epsilon prescription, except at the saddle points where all of derivatives vanish identically. Actually, the effect of doing so resolves branch cuts in the kinematic space. So for a generic S matrix, you would find that there are branch cuts that are overlapping on the real axis, for example, in the energy space. And if you track down what the effect of rotating the word lines is, they actually deform the branch cuts precisely in such a way that they tell you about the physical, they unravel the physical information about the scattering amplitude somewhere here. So for us, this is important because it actually guarantees analyticity close to the physical region. However, by itself, it does not imply anything about analyticity away from the physical kinematics. So for this, we need to do analytic continuation in external energies. Okay, so the trick is to do it precisely in such a way that we stay within the complexified light cone. In other words, that we do not violate on-shell conditions. So let me illustrate how this works at 4 point. Okay, at 4 point, we have 4 external momenta. So what we're going to do is we're going to go to light cone coordinates. So we have some plus and minus directions within the light cone. And you can always go to a frame in which the light cone coordinates of the particle 1 and 4 are directly opposite each other, like here. And likewise, those of 2 and 3 are directly opposite as well. Then what we would like to do, so this is a 2-2 scattering with 1, 2, and 3, 4 outgoing, 1, 2 to 3, 4. And then what we would like to do is we would like to rotate the energies of the particle 2 and 3 such that we go from future to the past light cone and vice versa. So the way that this can be done is we can use a small complex parameter z. And originally we started at z being equal to 1. And then what we want to do is analytically continue that to z equals -1. This is the effect of exchanging the energies of these two particles here. Awesome. So now the internal momenta, which are denoted with this with this notation, can be decomposed along those two directions. Okay, within the light cone, we can decompose it into directions proportional to P1 and those that are proportional to P2. So let me call the coefficients of this expansion by F and G. Now, as we deform the external kinematics with this complex parameter Z, the internal kinematics also inherits it here. Now we can ask what happens when we try to put this propagator on shell. In fact, it's really enough to look at the imaginary part of the on-shell constraint here. And it's easy to see that that is actually going to be proportional to F times G. This means that if there was an on-shell singularity along this path of deformation, it would have to be such that F is equal to 0, G is equal to 0, or both at the same time. Okay, this for comparing with this line, it directly means that all the internal propagators have to be aligned purely within the light cone directions with P2, P1, or perhaps they can vanish, their momenta can vanish in the light cone directions.
5 more minutes.
Okay. It's actually unknown if such anomalous threshold exists in an arbitrary theory. However, what we know now is that we can specialize to planar amplitudes, for example, in the large N QCD. Moreover, what we're going to do is we're going to specialize to processes in which all the incoming and all the outgoing momenta are consecutive with respect to each other. So this is one example of a Feynman diagram that we'll consider. It's actually very easy to see that the dangerous singularities can never appear for those planar amplitudes. This is simply because we can consider planar ordering 1, 2, 3, 4, and then we can ask what happens when you apply the momentum in one of these directions, P1. Then intuitively, on the perimeter of this diagram, the momentum has to flow in a specific direction, okay, as indicated with those arrows, consistent with causality. Now you can repeat the same argument for the momentum P2, and then what you find is that exactly the same holds, that the momentum along the perimeter has to flow in this specific direction. Okay, what this means is that if we consider some edges on the perimeter of the diagram, for them the coefficients of the expansion have to have a specific sign, and this is in direct contradiction with putting them on shell. This actually means that those anomalous thresholds do not exist. It guarantees analyticity when rotating from the past to the future light cones and vice versa. Okay, this is actually not yet enough. What you need to do is you have to compose what we've learned about avoiding real singularities and avoiding complex singularities. And if you compose this in a specific way, that I will refer you to the details into this paper, the effect of that is essentially analytic continuation between different crossing channels. For example, you can consider these group some particles into some set A, which used to be incoming. And the result of this procedure is that the particles become now A bar, the outgoing antiparticles with the opposite momentum. Okay, so what this gives us is analytic continuation between different physical channels. In other words, if this side of the equation exists, the S matrix in this channel, if it exists, then the S matrix in this channel has to also exist, and it's given by analytic continuation of the first of the left-hand side. Okay, this does not yet imply crossing symmetry, but crossing symmetry follows from several applications of this grouping of particles and crossing them in this way. And once again, you can consult the details in this reference. But the effect of that is that on the left-hand side, we have the same process with a particle n, and on the right-hand side, we have the same process with a particle n bar, so the antiparticle, with the planarity being preserved and all the remaining particles being preserved as well. So this is, in fact, the first realization of crossing symmetry, in this case for planar amplitudes at every order in perturbation theory, with any masses, with any spins and multiplicity, up to the caveats that I mentioned on the previous slide. So let me summarize. I've explained this age-old question about crossing symmetry in quantum field theories. First of all, I've outlined some of the difficulties that pose a challenge in non-perturbative approaches and the reason why that essentially failed in the last century. Then we proposed a new approach which analyzed singularities of the S matrix as the wordline saddle points. Then I've explained some of the potential obstructions that you can have in proving crossing symmetry. And then we've seen that for planar amplitudes, they do not exist, and therefore crossing symmetry in those cases is satisfied. So with that, thank you for your attention.
Thank you. Do we have questions? Yes, David?
Yes, the obvious question. What about the non-planar case?
Yes, so very good. You can let's look at this example. So we actually know that very similar arguments about just studying energy flows in the within the diagram, they actually guarantee crossing symmetry for many diagrams, such as this one. And I will not go into details, but basically there are infinite families of diagrams for which we know that they have to be crossing symmetric using exactly the same deformation as in the planar cases. But we don't know it for all. So I think for more or less all of the free loop diagram, up to free loops, there's no problems, and the questions are only about higher loop contributions.
Another question, Valence?
Have you thought about, so you have a conjecture that the, let's say, alphabet of singularities becomes infinitely complicated, at least in the massive case. What do you think about the massless case?
Let me first of all clarify the conjecture. The only thing that I mean here is that that the amplitude could not be written in a closed form. What this means is that I suspect that if we have these arbitrarily complicated singularities, roughly speaking, what happens, what you can think of, the way I think of the sort of arguments of logs and so on, is that they roughly correspond to the roots of these polynomials. So of course, if this polynomial is degree 5 and higher, then it just means that there is no analytic solution for the roots, and therefore there would be no analytic expression for the amplitude. So this is all I meant. I'm not claiming that there's an infinite, that the alphabet is infinite. And of course, things become, as exemplified in this case, things become much easier in the massless case. But I do not have anything concrete to say there.
Yeah, I was thinking more of the massless case with many legs, but anyway, yeah, I should have clarified.
Yeah, I don't have anything concrete to say there. But of course, Landau analysis in general will answer this question. So the question is, can we make it into an efficient procedure? And one of the directions, this was one of the motivations behind this work, to make the prediction for the alphabet of singularities sort of algorithmic.
Can you talk about the capabilities of that program?
We're not there yet, and sorry, we're not there yet in the higher like cases, and it's actually difficult to predict the capabilities of this program because it heavily depends on how complicated the answer is. For example, if the answer decomposes into multiple components like this one, then it becomes very efficient. But of course, it's very difficult a priori to predict for a given diagram how complicated this Landau discriminant will be. But we managed to cover many examples up to 5-point free loops where you have this kind of structure.
So in view of time, let's thank Sebastian again.